This video is entitled The Natural Log Function Differentiation. Now, logs, generally work in this process right here. You can always find sources if you need to review properties of logs, but how logs and exponentials relate to each other. And you see, so log of base a of x equals y. That's the equivalent exponential equation of saying a to the y equals x. And as logarithms are used to solve equations that exponential equations that could not be solved without them. Like for this one, 4 to the x equals 66. Well, we know it's at least 3 since 4 to the 3 equals 64, but it's less than 4, so x is between 3 and 4. But now you can apply any logarithm to this. We're using specifically the natural log, which is the log with base of the number e, which e we'll talk about in another video, another section. E is that exponential number e. So if you take a logarithm, you log both sides, it algebraically brings the exponent down. And that's in this case, since the exponent's a variable we're solving for, we need that to come down. And so in this case, the x would come down, and you would divide both sides by ln of 4. So technically, the exact answer is ln of 66 divided by ln of 4. That's the exact answer. And of course, you can see what it was if you wanted to decimal. Turns out being about 3.02. Now, the natural log function is defined as an integral. That's just the definition of it. But then there's what it is as a logarithm. It's just log base e. You don't have to necessarily know this integral definition, but I'm going to tie that in here in a minute with the derivative of what ln of x is going to be. Now, here's some basic log properties that I think are good to know. Well, I don't think you have to know the first one. Natural log of 1 is 0, but these are important. The natural log of a times b, and that would expand as many things in here that were multiplied. In this case, it's just two things multiplied, so it'd be ln of a plus ln of b. And then this property says apply natural log a to the n. It brings the n down, sort of like the example I showed over here. And then the log of a division is, in this case, natural log of a minus natural log of b. You subtract. Now, you have to be careful then that you don't make up properties that aren't true. Don't come up with something that's not really a log property. And this is what I'm showing right here in red, is that the log of a plus b or a minus b does not expand at all. It is literally right that you can't break it up. So don't try to do things that aren't allowed. You would just literally leave it as whatever it was. If it was the natural log of x plus 2, it just remains that. It doesn't change. Now let's look at using some of these properties just to sort of simplify. And I just showed the conversion for radicals, which you should already know by now with doing derivatives and antiderivatives, but I just wrote that property there again. So simplifying basically means, when we say simplify, is don't have any unnecessary products or divisions that can be broken down, and then no unnecessary exponents. And I'll talk about sort of by unnecessary here when we get to this next example down the page here. But for now, see, so the square root of x to the 5th can be written as x to the 5 halves. So natural log of x to the 5 halves equals 5 halves ln of x. Now all I did over here, this doesn't prove anything, but you can at least see that it's equivalent for this particular number. Here I used 2 as my x and showed that the square root of ln of 2 to the 5th is the same as 5 halves times ln of 2. They match. Obviously that's not required. Looks like I did the same thing right here with these numbers. So ln of x, y, z multiplied would be ln of x plus ln of y plus ln of z. All right, ln of x to the fourth, and this kind of goes back to something I mentioned in another video with trig functions, that when it's written like this, you're assuming that the x is raised to the power, not the natural log. So I'm just showing that these are equivalent forms, that this means ln of x to the fourth means that. Then you can bring the 4 down, but here's where students sometimes run into trouble dealing with logarithms. This next example, ln of x all raised to the fourth. That means the logarithm is raised to the fourth power. That's the same thing as this, if you wrote it this way. Well, either way, whichever way they're written, that 4 does not come down. Nothing happens to it, because it's only the argument of the function. If it's raised to a power, then that can come down. So you have to be careful and not get excited about automatically bringing every exponent down you see, because in this case it does not come down. Now let's take a look at this one. Now I'm going to teach you a little shortcut here, so you don't have to write out, you could do, ln of the top part minus the bottom part, and then you could split those up as plus and plus. But what you have to keep in mind here is, even though these are plus and plus on bottom, they would follow a minus sign. So it would distribute, the minus of two things added together, like the negative of parentheses a plus b is negative a minus b. Well, anyway, long story short, to make this quick, is anything, if you're dealing with a fraction, anything in the numerator will be positive, anything in the denominator will be negative. And that just saves you a lot of time and effort. So both these two terms on the bottom, x plus 4 squared and sine of x, both of them would have minus. Like I said, even though it's plus between there, when you expand them, they would still follow an overall minus there. So it makes them both negative. All right. So let's see. So we break it up. Top plus plus minus minus. Plus plus minus minus. Ln of x to the fifth. Ln of x squared minus 3 to the 1/2. Minus ln of x to the 4 squared minus ln of sine of x. Well, we can bring this 5 down. Next term, we can bring the 1/2 down. So when I talk about bringing down all exponents, that you're allowed to bring down, that's the key, is you can't, in other words, you can't go in the parentheses of this second term and grab that 2 out of there. Now you can't split that up. As I said earlier, plus and minus, you can't split that up, so you just leave it alone. That's it. Only that 1/2 right there comes down. This 2 would come down, and then nothing happens here. Bucky gives approval there. Thank you, Bucky. Now the derivative of the natural log function. The derivative of natural log of just x itself would be 1 over x, assuming x has to be a positive number here. So if you're dealing with variables, you'll just assume that that's true, because the domain of natural log is only for positive numbers. You can't take the log of 0 or negative. You can try that out in your calculator and see what happens. It'll give you some sort of error. But let's see. Let me come back up here for a second to show you something. Now this goes back to something in a previous section called this, I believe it's 4.4, the second fundamental theorem of calculus. That if you wanted to take the derivative of this right here, or the derivative of this, we're saying ln of x equals this, and you want to take the derivative of this, all you have to do is replace x where t is. Now, if it's just x, that's all you have to do is replace x where t is. If it was like x squared, you'd have to put the x in there and then also multiply it by the derivative of x squared. But since the derivative of x is 1, you don't have to do anything. So literally, using the second fundamental theorem of calculus, the derivative of this integral would be 1 over x. So if ln of x is defined as this integral, therefore its derivative would be 1 over x. All right. Now, of course, we'll have ln of x, but more commonly, the problem will have u will be some sort of function of x. So like some of this other stuff, like this last problem here, like there's ln of x, but here's ln of x squared minus 3. So that would be your u. The next one's ln of x plus 4. That would be your u. And for this one, the u would be sine of x. So when it's x, it's just 1 over x. But when it's u as a function of x, it's 1 over u times the derivative of that u. So which you can also just write as u prime over u. So it's the derivative of the argument over the argument of the natural log. So it's not too bad. So it's either 1 over x or it's either u prime over u. Okay? And there's what I was saying verbally. I want to explain this again, but using the second fundamental theorem of calculus. Already done that one. Now the whole purpose of that log simplification, like I did there a minute ago, we'll look at some of these problems. I'm not sure if I brought that problem in as an example. Probably wouldn't have gotten that involved for a test, but let's just come back up here. If you were going to take the derivative of this without simplifying, the simplifying makes the problem so much easier. This would be a mess here because you would have a quotient rule and then product rule buried within the quotient rule. But using log properties to split them up into individual pieces is just delightful, because then you just take the derivative of each individual logarithm. It's so much easier. I promise you that doing these 4 individual derivatives right here would be a lot quicker than doing the derivative of all. So basically it would be the derivative of all this written over all this. I mean, what a mess. So much nicer. So like I said, we're going to, simplify before differentiating. That's kind of understood, even though the problem doesn't have to tell you that. But technically you could do it without it. But like I said, you ought to just plan on doing it. All right, so this is x squared minus 4 to the 1/2. So the 1/2 comes down. So keep in mind, this was just, I'm not, till I write my y prime, I haven't taken the derivative yet. I've just used the log properties. Now I'm going to take the derivative of this expression right here. We're looking for u prime over u, with the u being x squared minus 4. So we have a 1/2 here, so that stays there. So basically the derivative of this would be the derivative of x squared minus 4 over x squared minus 4. Well, the derivative of x squared minus 4 is 2x, and there's x squared minus 4. Now we have the 1/2 there, so you can cancel the 2's out. It's not too much trouble. So the simplified answer would be x divided by x squared minus 4. That's what we got right here, and that's what Maple got. So that's terrific. Okay. Now how about this, the natural log of 2x over x plus 3? We'll use division first. We'll split this up. So we have ln of 2x minus ln of x plus 3. Now you could technically split up the ln of 2x like I did right down here. That's what I'm writing right there. But you can actually get away without doing that. You can if you want to. But it's always interesting when I'm doing a face-to-face class, after we saw the ln of x was x, I'll sometimes then say, before I do this problem, I might write another one, on the screen and say, okay, what's the derivative then you think of natural log of 3x? A lot of people will react 3 over x. That's not correct. The derivative, in this case, ln of 2x, it's the derivative of 2x over 2x. So the derivative of 2x is 2 over 2x. The 2's cancel. It leaves you 1 over x. In fact, I wrote this as a rule right here. If this assumes that a times x is greater than 0, the derivative of natural log of any coefficient of x, so if it was like 6x, it would still be 1 over x, no matter what that coefficient is, as long as it's positive. And okay, let me finish the rest of the problem then. So now the derivative of ln of x plus 3 would be the derivative of x plus 3, which is 1 over x plus 3. So there you go. We don't have to worry about getting a common denominator or anything like that and merging this together. That's a perfectly good answer. right here. Well, let's suppose that you did split this up one more step further, and you wrote ln of 2x is ln of 2 plus ln of x. Well, here's another reason why the derivative is 1 over x. Because the ln of 2 is just a number, just a constant. So its derivative would be 0, then the derivative plus the derivative ln of x, which is 1 over x. So there you go. You get 0 plus 1 over x makes it 1 over x. So just another reason that's true. Terrific. Alrighty, let's say f of x equals ln of x all cubed, not the ln of x cubed. The ln of x cubed. So this one, we don't really use log properties as much as we kind of treat this as a chain rule. Now you can do this without writing all the stuff I wrote below, but I kind of wanted to write this to sort of make sense out of it. So if I let u be ln of x and f of u equals u cubed, that means the derivative of u cubed would be 3u squared times u prime. Now we can go back up here. So all you really had to do, without writing all this notation, just, write your f prime of x there, of course. But you bring the 3 down, you drop the 3 from down to 2, and then you take the derivative of the inside, which we're now learning natural logs. The derivative of natural log would be the 1 over x right there at the end. So this was basically just a general power rule derivative. We're now learning, natural logs. So the derivative of natural log of x is 1 over x. So that's all I really boil it down to. Now here's the difference between this and suppose it would have been ln of x cubed. Well, if it's ln of x cubed, bring the 3 down, which makes it 3 ln of x. And then you take the derivative of 3 ln of x. And the 3 would stay there. The derivative of ln of 3x would be 1 over ln of x would be 1 over x. So 3 times 1 over x makes 3 over x. So that derivative would be 3 over x. But the derivative of ln of 3x would still be 1 over x, like I explained before. But this one, yes, you bring the 3 down. Or if you didn't bring the 3 down for this one, I would recommend doing that every time, though. But just in this case, I'll mention it would have been simple enough. You could have said the derivative of x cubed, which is 3x squared, divided by x cubed, and that would have simplified down to still 3 over x. All right, so we have t cubed. Now it's a function of t. So y equals t cubed times natural log of the absolute value of cosine of t. The absolute value, sometimes you'll see that written with natural log, and the purpose of it is to guarantee that the quantity is positive for the inside part here, but it doesn't affect anything mathematically, but it just guarantees positivity of the inside quantity. So here's a refresher for the product rule. Wrote that out to the right. Obviously, if you do it in the other order than I do it, that's okay. You got a little flexibility on the order. And so we have the derivative of t cubed would be 3t squared. And then times g, which is just the ln of cosine of t, plus the f, which is t cubed, times the derivative of ln of cosine of t. Well, the derivative of ln of cosine of t will be the derivative of cosine of t divided by cosine of t. So it's cosine of t prime over cosine of t. So then we want to take the derivative of cosine of t, which is negative sine of t. Now notice that's very important that I have parentheses wrapped around there. Very important. Unless you go ahead and bring the negative out first, then you don't need the parentheses. But otherwise, it would look like subtraction. But if I move the negative in front, then I could drop the parentheses like I did right here. So that leaves you sine over cosine, which, Bucky says this is the correct answer right here, and Bucky's right. That would be fine mathematically, but just because it was so easy to rewrite sine over cosine as tangent, I just went ahead and did that. That's the only reason. But mathematically, it was right here at the Bucky step. But so it just became minus t cubed tan of t. I put this in Maple. I started typing this and realized I'd put X and realized the problem here said T. I just didn't feel like redoing it. I just left it. But anyway, obviously if this was T, it's the same answer. They have yeah, they did this one. They did not reduce the sine over cosine, which actually didn't have to, but change the variable from T to X. Same answer. Very good. All right, this one's interesting. ln of ln of x. So what you do is let the inner ln of x be u, then that gives you ln of u as the function you're taking the derivative of. So ln of u, which I have it written right here also, obviously applies to both of these. ln of u, the derivative ln of u would be u prime over u. So what the answer for this one would be, it's the derivative of ln of x over ln of x. So it's 1 over x divided by ln of x. Now this is correct, but you also, if you're, especially if you're looking at this as multiple choice, you'd probably see the x written down on the bottom and look like this. But obviously this they're mathematically equivalent. Just drops the x down to the bottom. All right, so that's good. That's correct. How about this next one? ln of x plus the square root of 4 plus x squared. Now taking the basic derivative is easy enough. It would be the derivative of everything in the parentheses divided by everything in the parentheses. So everything in the parentheses here, x plus the square root of 4x squared. 4 plus x, square root of 4 plus x squared is right here on the bottom. And then the derivative of x is 1. So you see I have it written over here. You take the, so the 1/2 will come down, changes the exponent to negative 1/2 when you subtract 1. Derivative of the inside is 2x. So the 2's would cancel. And you're left with this. Now suppose we want to simplify this. Now for exam purposes, wouldn't be necessary, but I'll explain here in a second why I did it for this one after we did it. So I just took a term for, I dropped this negative back down and made it a fraction to make it easier to visualize. So I multiplied top and bottom by this term right here to turn it into one fraction instead of a complex fraction, and that kind of tidied things up, pretty nicely. I'm not saying they would always do this, but yeah, and you end up getting a situation where these terms cancel one, and then you're left with just this term on the bottom by itself. And so we end up with this answer right here, which you see. So Maple has my answer just written a little bit differently, but like this as this answer right here. Just put the radical back in there, and then I said simplify, and it turned it into this answer. Well, the reason why I did this is not for something you would have to do on an exam, but the reason I did this is because I want to show you that when we start doing more challenging integration later on, for those of you taking Cal 2, we would learn how to take this function right here that was the answer and take the antiderivative of this back in and turn it back into that problem right there. But that's a Cal 2 exercise, so nothing you're going to have to worry about in this class. So that's the reason why I did that. Now this next topic, logarithmic differentiation. You might be thinking, well, isn't that what we've been doing, logarithmic differentiation? Technically, no. We've been finding differentiation of the natural log function. In another section, we're going to look at the differentiation of other log bases, like if it was just log base 10 or log base 2. No, this logarithmic differentiation is not differentiation of a logarithm. It's a technique to take derivatives of any functions using logarithms to make them a little simpler to deal with. So this is a technique. It's a process. All right, let's see what we got here. Let's say we had this big old mess right here. Y equals all this stuff right here. Kind of messy, right? And we want to take the derivative of it using this technique. And so this technique says you apply natural log to both sides. So y becomes ln of y, and then becomes ln of everything on this right side. So the purpose of that is, like I kind of mentioned this a little while ago, but now we're going to see it in action, is using the logarithm, it splits it up into individual pieces, which makes the derivative actually simpler to handle. So, and remember I told you that anything in the numerator is going to be plus, anything in the denominator will be minus. So the x cubed and the 2 minus x to the 3 halves are going to be positive, and then the x plus 1 squared, then we'll have a minus sign in front of it. So there's the split up. They all have natural logs. And then the next step, nothing's happening on the left side yet. The next step is I'm simplifying where I can here, so the bringing down exponents. 3 comes down here, 3 halves comes down for the middle one, 2 comes down. Now we're taking the derivative of both sides with respect to x. Now back in the section on chain rule derivatives, that anytime you take the derivative of a variable that doesn't match, you have variable mismatch. It's essentially a chain rule. Just in other words, like the example, if you're taking d dx of u cubed, let's just say y equals u cubed, and we've done this with natural log in this section, where u is a function of x. That's the key. U is a function of x. Y prime would be 3u squared, but it'd be u prime being du dx. So what's happening here is that, and this will happen every time, then it becomes essentially a no-brainer, because you don't have to even think about this anymore after this time. It becomes automatic. The derivative of natural log of y, because you're taking it with respect to x and not y. See, the d dx of ln of x would just be 1 over x, and that would be the end of the story. But here, just like you were taking the derivative of u, ln of u, same thing. The derivative of ln of u would be u prime over u, so ln of y would be y prime over y. Only ln of x would be 1 over x. So let's see what we have on the right side. So that becomes y prime over y every time. We have 3 ln of x would be 3 times 1 over x, so it's 3 over x. So the middle term would be the derivative of 2x minus 3 over 2x minus 3. So that gives me 2 over 2x minus 3. Derivative of x plus 1 is 1, divided by x plus 1, with a 2 in front, so I cancel those 2's. Now ultimately, the idea is we're getting y prime in terms of x. So what I'm doing is I'm bringing this y up to the other side. Oh, here I'm sort of mentioning the chain rule idea here. We even put in a happy face there just for fun. So obviously I was just showing you how the variables match up there. So 1 over x. But anything else, y would be y prime over y. Happy face as a function of x would be happy face prime over happy face. Well, here, all you do in the last step is you have the y comes up, and then just replace y with all this right here, and that's it. You don't have to distribute or simplify or anything like that. That's the answer. Now, yes, this algebraically would be equivalent. It'd be the same answer, but it would look totally different if you did this derivative without using logarithmic differentiation. Obviously, the answer would look completely different, but if it's done correctly, it would be mathematically the same. So you see, all I did here is replace y with what it was defined as originally. There's y right there, and that's it. We don't care about simplifying this or anything. That's good enough. So let's see what we have here, and that's it for that one. Here's another one. We're going to differentiate y equals x to the 5th tan of x over x squared plus 3 to the 4th. So I'm going to ln both sides. So I have ln of y on the left, and then you see I did this kind of in one step. So once I wrote the ln, I kind of split it up. 2 pluses on top and a minus on bottom, plus, plus, minus. All right, so you got this business right here. Bring the 5 down. 5 ln of x. And let's see what we have here. You can't simplify that one, and then this one you can bring the 4 down. So brought down all, the x squared has to stay there. You cannot break this up at all. You have to resist the temptation of breaking that up. It will stay, but the 4 comes down. And let's see. So the derivative of ln of x is, so ln of y, of course, like I said, that's always y prime over y. So it becomes sort of automatic. You don't have to think about it. So let's think about the right side. The right side then becomes, the derivative of ln of x would be 1 over x. And then the derivative of ln of tan of x would be the derivative of tan of x over tan of x. Well, the derivative of tan of x is sec squared. So sec squared over tan x. There we go. And then the next one, the derivative of x squared plus 3 would be 2x over x squared plus 3 with the 4 there. So I just put this together as 5 over x. I went ahead and multiply the 4 times 2. It would be 8x over x squared plus 3. And then let's see, this is the next step. I guess technically, you could do these 2 steps at once. When you bring the y up, it's the same thing then as replacing y as what it was originally. So if you felt comfortable enough, you could go from this step down to the last step. But I brought the y up to put the extra step in there and then replace y. So you don't have to, there it is again. You don't have to distribute, multiply. You leave that answer just like it is. Perfect. Terrific. And this this next one, yeah, obviously you would not do this, but I'm just kind of sort of showing you. This is not a mathematical proof, but I'm giving you an example of the reason why that technique is okay. Like I said, this isn't a proof, but it better work for this example I'm using for sure. We know what's wrong otherwise. So y equals x squared. Yeah, so okay, of course, to find the derivative of that, we know it's 2x, so we don't really need to do anything too fancy. Well, let's show this technique. She'll generate that same answer. So I'm taking the ln of both sides. There it is. ln of y equals ln of 2x squared, which then allows the 2 to come down. So it's 2 ln of x. So if I go d dx to both sides, we know the ln of y becomes y prime over y. The derivative of 2 times ln of x would be 2 times 1 over x, so it's 2 over x. Then we need to bring the y up, which I did right here. Bring the y up here. Replace y with what it was originally. Y is x squared. So x squared times 2 over x equals 2x. So therefore, the derivative of y equals x squared, which you already knew, is 2x. But just want to show you how that worked using logarithmic differentiation. So this is example we had earlier here. Let's go back up here and show you. Oh. No. Oh, it was only simplifying. Where'd it go? Is that one? I don't know. So it said it's from somewhere earlier. It looks familiar. Let me try one more shot at it. Try to figure out why I missed it here. Oh, there it is. Right there. So you see it's already simplified. So this problem then is not, this is not logarithmic differentiation. So this is just a revisiting that simplification problem. So you see the logarithmic differentiation basically will not start out with a log right here. That's the key. Like so you saw this one. See that you didn't start out with a log, right? I guess technically you could have a log function over there on the right side, but you don't have a log of an entire thing there. So it wouldn't be wrong, or this one here. You don't have a log of all that. So I don't like this confusing. This is kind of just another example. So we're just finding the derivative of a logarithm. So it's already split up for us that we had. So therefore, y prime, you just take each of these derivatives. So that'd be 5 over x. The derivative of x squared minus ln of x squared minus 3 would be the derivative of x squared minus 3, which is 2x over x squared minus 3. And then the derivative of x plus 4 would be 1. So you already have a 2 there. So of course 2 times 1 is 2 over x plus 4. Then the derivative of natural log of sine of x would be the derivative of sine of x, which is cos of x, over sine of x. So, okay, yeah, I guess, so this is right. Somebody could technically rewrite that as cotangent x if they feel like it. I guess I could have done this and I didn't do this, but obviously this isn't wrong, but you could certainly cancel those out if you wanted to. But it's not mandatory. But that would be correct for the derivative of all this mess. So, well, that concludes the video for logarithmic differentiation.